Greetings! In today's video I'm going to be talking about the Affine Cipher. First off, at its core, the Affine Cipher is just a modified version of the Caesar shift cipher, but with one additional twist. As we'll see shortly, not only does the Affine Cipher shift letters in the ciphertext, it also performs its encoding by first converting letters into numbers, passing those numbers through a simple mathematical function, and then converting the resulting numbers back into letters. So with that, let's take a closer look at the Affine Cipher. The Affine Cipher is one of many ciphers that falls into the monoalphabetic substitution category. This means each letter in the plaintext message is converted into a single letter in the ciphertext. And as I already mentioned, when using the Affine Cipher, the encryption is done by converting letters into numbers, passing these numbers through a simple mathematical function, and then converting the resulting numbers back into letters. To decrypt, the same process is performed, but this time we use the inverse of the encryption function, and I'll get into what that means in a bit. So what exactly are these encryption and decryption functions I keep talking about? Well, to start, here's what the encryption function looks like. This function works by acting like a simple shift algorithm, with the A variable acting as a multiplier for the shift, and the B used as an additional shift modifier. Everything inside this function is contained within a specific range indicated by the modulus operator. And to decrypt, the function looks about the same, except it moves everything in the opposite direction. For this reason, this function is said to be the direct inverse of the encryption function. Now, as you might have noticed, both functions contain the same set of variables, which means before we can go ahead and use these functions, we first need to understand what these variables mean. So let's take a look at these now. There are 4 variables contained within each function: A, B, M, and X. Right now, I'm only displaying the encryption function for reference, but the same information applies to the decryption function. The first 2 variables in the list, A and B, combine together to make a 2-part encryption key. These values will need to be generated before we can encrypt or decrypt a message, and we'll see how this is done in a few minutes. The next variable in our list, M, refers to the length of the alphabet which was used to encode our secret message. And finally, we have the X variable. This is a unique variable because while the other variables never change throughout the encryption or decryption process, the X variable is assigned the values of different numbers representing each letter in the message. Don't worry if this doesn't make any sense right now, we'll get into this later in the video. So with that out of the way, let's see how the Affine Cipher can be used to encrypt a secret message. When we look at doing the encryption, there are 4 main steps that need to be performed. The first step is to determine the length of the alphabet used to create the secret message. The next step is to generate the encryption key values, which are used by both the encryption and decryption functions. The third step is to convert all the characters in the secret message into their numerical equivalents. And finally, we take all this information that we've gathered so far and perform the encryption action once for each character in the plaintext message. The numerical result of the formula is then turned back into a letter, which we add to the ciphertext. Let's take a closer look at how all of this works. So once again, the first step is to decide which alphabet we plan on using to write out our message. Now in most cases, the standard 26-character English alphabet will suit our purposes. But we don't need to restrict ourselves to just this set of characters. If we wanted to, we could, for example, create an alphabet that contains all uppercase, lowercase, and numerical characters, or we could even use the alphabet of another language. The important thing to note here is whatever the length of the alphabet used, we record that value in our variable M. For the rest of this video, I'm going to be using the standard 26-character English alphabet, so we'll set M to 26. Once we've decided the alphabet, the next step in the encryption process is to generate the encryption key. The key is separated into 2 parts and is represented by the values stored in A and B. We can choose whatever number we want for both keys, so long as they both follow a set of rules. For the first rule, since both keys are restricted by the modulus operator, this means they have to fall within a range of 0 to m-1. With a 26-character alphabet, for example, the values A and B would have to fall within the range of 0 to 25. The A key also has one additional rule it needs to follow. The number you choose needs to be co-prime with the length of the alphabet. Numbers are co-prime when they only share a common factor of 1. We can see how to work this out by first determining the common factors for the value m, which for the example of m equals 26 are 1, 2, 13, and 26. Next, we create a list of numbers from 0 to 25 and start eliminating numbers that are not co-prime with the common factor list for m. We can start by skipping the number 1, since this number is co-prime with every number, and move on to the next number, the number 2. We look for any number in the list that also has a common factor of 2, and since every even number is divisible by the number 2, we can remove these and move on to the next number in the list. For the number 13, the only number in the list that shares a common factor is itself, so we eliminate the 13 from the list. Finally, there's nothing in the list that shares a common factor of 26, so we finish here. The end result is a list of numbers that are co-prime with the length of the alphabet, and it's from this list that we must select a value for the variable a. We now have enough information we need to generate our key, so for this demonstration, I'll go ahead and choose two numbers, 15 for A and 23 for B. These two numbers will now represent our encryption key. And now that we have the encryption key, the third step in the encryption process is to convert all of the letters in the plaintext message into their numerical values. To do this, we first create a table that pairs each letter in the table with its equivalent number, starting at 0. Next, we write down the plaintext message we want to send out to the message receiver, and convert each letter in the message into a number using the lookup table. So, for example, the first letter here is W, so we write down a 22. The next letter is E, so it becomes a 4, and so on and so on. This list of numbers will later be assigned to the variable X when we start iterating through each letter in the encryption process. So let's see how that's done. As I mentioned, for this process to work, each X value from the set must be run through the encryption function one at a time. This will generate an output value which will later be converted back into a letter. So for example, the first number in the set is a 22. If we take this number and assign it to the X variable and run this number through the encryption equation alongside the other variables, we come up with the number 15. This number is recorded and we iterate on to the next number. In this case, that would be the number 4. Again, we assign this number to X and run it through the encryption equation and come up with the number 5. This continues in a loop for each numerical value in the set until we reach the end of the message. And with our new set of numbers calculated, the final step is to convert these new numbers back into letters using the same approach as before. We pull up the lookup table, take the first number in the message, 15, and convert it into the letter P. The second number, 5, becomes an F, and again, this repeats until the end of the message. And there you go. We now have an encrypted ciphertext message which can be passed on to our message receiver. So that's all fine for encryption, but what about the decryption? So far, we've encoded our secret message, which has been sent to the message receiver. Now, we need to come up with a way for the message receiver to decipher the text. The good news is, we've already done most of the work needed to decrypt the message. We'll assume for now the receiver already knows the values for the encryption keys, as well as the length of the alphabet used to create the message. So what's left for him to do? There are 3 things the message receiver will need to do in order to decrypt the message. First, they'll need to convert the letters of the ciphertext back into numbers. And if you're wondering why we bother sending letters to the receiver instead of their numerical equivalents, especially since the receiver is going to have to convert these letters back into numbers anyway, try thinking of it in terms of how a message is likely to be transmitted. Before modern computers became a thing, messages would likely be sent out on a piece of paper or transmitted over a wire. There's less room for mistakes when transmitting single character letters than you would with multiple digit numbers. Either way, once the receiver has converted these letters into numbers, the next step is to run each of these numbers through a mathematical decryption function. If done properly, this should produce the original list of numbers for the plaintext message. Finally, the receiver will need to be able to read this message, so he converts the decrypted numbers back into their original letters, which gives him the plaintext message. So let's take a look in more detail on how this is done. Like before, the first step the message receiver must do is take the encrypted ciphertext and convert the characters into numbers using the same lookup table as before. And as before, the list of numbers will later become the X values when we iterate through the decryption process. So we take the values that we've gathered so far and try to pass them into the decryption function. But hold on a second, we have a bit of a problem here. While it may not be obvious, we're missing a piece of information needed to decrypt the message. If we look at the first term in the equation, we see that we need to find the value for a raised to the power of -1. And you might think, what's the big deal? Any number raised to the power of -1 is just its inverse. So if our a value is 15, a to the power of -1 is just 1 over 15, right? And normally you would be correct, except in this case there's a little gotcha that comes when we start to employ modular arithmetic. To explain what I mean, I'll do a brief demonstration on what happens when we blindly plug in the direct inverse into the equation. But first, I'll need to grab an X value, and since the first number in the list just happens to be a 15, which is the same as our A value, I'll grab the second number from the list since I don't want to get anything mixed up. This means X will equal 5 for this example. So let's see what happens when we plug these numbers directly into the decryption function. As we can see, the first term is the inverse of A, which is 1 over 15, the X value is 5, the B value is 23, and finally the length of the alphabet M is 26. So far, so good. But let's see what we get when we run these numbers through a calculator. The number we end up with is 24.8. Now, that doesn't seem right. Not only is this not the right answer, it also has a decimal place. For this to work, we need to be able to convert the answer from a number back into a letter using the lookup table. And for that to happen, we need a whole number. So what happened here? Well, if you take a closer look at the fraction, you'll see what we're doing here is basically simple division. And whenever you use division and a modulus operator in the same equation, funny things start to happen. This means we need to come up with a different number, one that is equivalent to the inverse of A, but also respects the modulus operator in the equation. To do this, we'll need to take a closer look at some modular arithmetic. If you happen to be familiar with number theory, you may have heard of the term modular multiplicative inverse. Now, I don't want to go over every detail of the modular inverse in this video. There is a little bit of effort involved in understanding how this works, and there are a lot of resources available if you're interested in finding out more details. But since this is important to the Affine Cipher, it does warrant some further discussion. The good news is, we don't need to know how to solve the modular inverse on paper. Fortunately for us, there's a quick and easy shortcut we can use instead. So let me start off by providing a quick summary of what the modular multiplicative inverse is, and then we can take a look at that shortcut. The modular inverse starts with the premise that if you multiply a number by its inverse, the equation equals 1. So for example, the inverse of 3 is 1/3, and if you multiply 3 times 1/3, you get the answer 1. But as I mentioned before, we can't use a fraction here because of modular arithmetic, so what we need to do is come up with a whole number that is still the inverse of our number, while also respecting the modulus m. What we're looking for here is an answer that is equivalent to 1, represented here by the triple equal sign. Again, this is not meant to explain everything in detail. I am kind of glossing over everything here, but it does provide us with a foundation to start looking for an answer. So let's take a look at that shortcut I was telling you about. The shortcut starts off by recognizing that the modulus m limits any value inside the equation to the range of 0 to m-1. We saw this before when we were generating the encryption keys A and B. This means the inverse of A must also be some number that falls within this range. And since this number is relatively small, this gives us an easy shortcut to solve this problem without having to resort to things like the Euclidean algorithm. Since the inverse value can only go from 0 to m-1, and in our case that would be 0 to 25, we can brute force our way to an answer by creating a table and assigning the number set to the inverse of A. So once we have our table, the next step is to iterate over each number and solve the modular inverse equation. And to make things easier to understand, I'll start off solving the equation by beginning with the part inside the parenthesis. Here, we multiply the value A, which in our case is 15, by each number in the table. And as you might suspect, this gives us a set of numbers that are factors of 15. Next, let's iterate over the table once more, this time factoring in the results from the second row and solving for the modulus 26. When all is said and done, we end up with a variety of different answers, but remember, we're only interested in the answer that is equivalent to 1. We look through the table, and lo and behold, we have a hit. When a to the power of -1 equals 7, the equation comes out equivalent to 1. This means when a equals 15 and the modulus m equals 26, the modular inverse of a is 7. And now that we have all of the numbers we need to solve our decryption function, we can go back to decrypting the secret message from before. To decrypt the message, we do the same thing as with the encryption, except that this time we use the decryption formula. When we plug in the first value into the equation, in this case 15, we run the numbers and come out with an answer of 22. The next number 5 becomes a 4, and we continue to iterate over the remaining numbers in the secret message until they've all been deciphered. And as you may have guessed, the final step is to take the numbers returned by the decryption function and turn them back into letters. We once again pull up our lookup table and start mapping the numbers. The first number 22 becomes a W, the second number 4 becomes an E, and again this is repeated until the end of the message. And after all of that, our message receiver has the secret message. So far, we've covered encryption and decryption for the Affine Cipher. In the last part of this video, I want to spend some time going over a few of the weaknesses of the Affine Cipher. Now, when you look at it, there are three primary ways you can attack an Affine Cipher. There are other methods you can use, but these three are generally the most effective. The first method is through a simple brute force attack. The second method uses a frequency analysis attack, and finally, the Affine Cipher is most susceptible when solving simultaneous equations. Let's take a closer look at each of these methods and see how they work. The first method, the brute force attack, solves the problem by going through every possible permutation of the encryption keys and using each key to try and decipher the secret message. So, for example, since the Affine Cipher uses two encryption keys, A and B, we start off with A equals 1 and B equals 1 and attempt to decrypt the message using those keys. If that fails, we move on to the next iteration with A equals 1, B equals 2, and try again. This continues on until we finally land on the combination of key pairs that gives us the correct answer. So the question is, how much effort is involved when using the brute force method? To understand this, we first need to know how many possible permutations there are for the encryption keys. As I mentioned before, this cipher relies on two keys which must follow a certain set of rules. In each case, both key values are restricted by the modulus operator, which limits them to a range of 0 to 1 minus the length of the alphabet. In addition, the A key must also be co-prime with the value of M, and as a reminder, here's a list of values we came up with in a previous slide. Altogether, when we're using a 26-character alphabet, there are 12 possible keys for the A variable and 26 possible keys for the B variable. Multiply these together and subtract by 1 because we start counting from 0, and you get a grand total of 311 possible encryption keys for the Affine Cipher. This means the Affine Cipher is a little more secure against a brute force attack than the Caesar shift cipher, which only has 25 possible permutations, but nowhere near as secure as the deranged alphabet cipher, which has keys numbering in the range of 10 raised to the power of 26. Again, this answer only applies when m equals 26, but regardless of the length of the alphabet, it wouldn't take much effort to crack the Affine Cipher with the brute force method. So moving on, the next form of attack is one that affects all monoalphabetic substitution ciphers and is called the frequency analysis attack. Frequency analysis is a rather large topic all by itself, and I've gone over it in more detail in other videos, but I'll provide a quick summary of it here. In a nutshell, the frequency analysis attack relies on the fact that certain letters appear more often than other letters within a given language. In the English language, for example, the letter E stands out as the most likely to appear in any given piece of text, while the letter Z is the least likely. You can see here the distribution chart for each letter in the English language, and at the bottom, the order of letter frequency from the most frequent to the least frequent. So how does this help us crack the Affine Cipher? As with any substitution cipher, letters in the plaintext message always map out to the same letter in the cipher text. As we see here, when we look at any occurrence of the letter W in the plaintext message, it always maps out to the same letter P. And the same logic applies to the other letters in the message. Of course, this only pertains to this particular set of encryption keys. If the user were to change the values of the encryption keys, the letter mappings would change as well, but the letters in the plaintext would still continue to map to the same letters in the cipher text. When an attacker uses frequency analysis, they're able to identify letters within the cipher text that appear more frequently than others. In this example, you can see that the letter F appears more often than other letters in the cipher text. This gives the attacker a clue which he can use to guess his way to a solution. Since F is the most common letter in the cipher text, there's a strong possibility it could translate to the letter E. It may not, but it provides the attacker with a good guiding point. Of course, this is all oversimplifying the process a bit, and you don't always get the answer right on the first try, but you get the idea. But with that, let's take a look at the final attack. The final method of attacking an Affine Cipher, and possibly its greatest weakness, relies on using simultaneous equations to mathematically determine the values of the encryption keys. Simultaneous equations, sometimes also referred to as system of equations, relies on the fact that two equations that have a common solution can be used to solve for the unknown variables in each equation. And in case you've forgotten what this looks like, here's a quick refresher. When we use simultaneous equations to solve for two or more unknown variables, we start with an initial equation and look for a second equation that shares the same set of unknown variables. And if we happen to plot both of these equations on a graph, we can take a look at both of their lines. If both lines on the graph happen to intersect at a certain point, we can use the xy values of the point of intersection to solve for these two unknown values. Now, we won't be using graphs to help us break the Affine cipher, but the analogy here helps us understand why this method of figuring out the encryption keys works so well. As long as the two equations have the same values for the unknown variables, and there is an intersection between the two equations, we can use simple algebra to help us find these unknown values. We can also solve simultaneous equations mathematically, and there are a few approaches we can use. The method we'll be most interested in today is called the subtraction method. This method is only effective when both equations happen to contain a similar term. We can use subtraction to eliminate this term and isolate the other unknown variable. Here, in this example, 2x minus 2x equals 0, thereby eliminating it. 3y minus y equals 2y, and 13 minus 7 equals 6. If we solve for y, we get the answer 3. We now know the value of one of our unknown variables. To find the value of the other unknown, we simply substitute y into one of the equations, and it doesn't really matter which one, and then we solve for x. We now have both the x and y values for each of these equations. And as you can see, it's a simple process, so let's see how this can be used to break the Affine cipher. For this attack, we'll be focusing on the encryption function to build our two simultaneous equations. But before we can use this attack on the Affine cipher, we first have to meet two conditions. First, the attacker needs to know the length of the alphabet used in the message. In most cases, you can assume it's the standard 26-character English alphabet. However, there is no guarantee the message writer didn't use a longer version of the alphabet or they wrote it in a different language. This is a small step you need to figure out, but it's still an important one. For now, we'll stick with the standard 26-character alphabet and move on. For the second rule, we need to know the letter mappings for at least two letters in the message. We can go about finding these two letters using other methods like frequency analysis or just plain old guessing. But either way, we need to know the mappings for at least two letters in the message. And before we get to the example, let's just take a quick second to remind ourselves exactly what we're looking for here. The purpose of this attack is to figure out the unknown values for the two keys used to perform the encryption. Again, these keys are represented by the letters A and B. Earlier in the video, the keys were assigned the arbitrary values of 15 and 23. Of course, the attacker doesn't know this, so let's see if our attacker can use basic math to help him find this out. To start, as I mentioned, we'll need the mappings for at least two letters in the message. So let's pretend the attacker has somehow divined that the mappings for the first word, WE, map to the letters P and F. Next, we'll need to convert these letters into their numerical equivalents. Since the encryption equation is being used here, the numbers from the plain text will be the x values for the two equations, and the numbers from the cipher text will represent the results of that equation. And again, the length of the alphabet M is 26. So we now have everything we need. Let's build our two equations. You can see here, we've taken the numbers and created two different equations. Since they both use the same encryption keys, this means that the values of A and B must be the same for both equations. Let's start figuring out what those two values are. Like before, we use the subtraction method to solve for one of the unknown keys. We take one equation and subtract it from the other. Here we see that 15 minus 5 equals 10, 22a minus 4a equals 18. The two b's cancel each other out and the mod is just carried through. We're now left with one variable a, so let's solve for it. We can see that when we solve for a, it comes out to 5/9 mod 26. So let's take a closer look at how we can break this number down even further and come up with a value we can use. Now, if you look at the number 5/9, this is the same thing as multiplying 5 times 1/9, and 1/9 can be rewritten as 9 to the power of -1, and there's that inverse again. Since the inverse is being affected by the modulus operator, this means we're going to need to pull out our trusty modular inverse equation once again. And because we're trying to replace the inverse of 9, this means our formula will end up looking something like this. Once again, we need to find some value that will come out to the equivalent answer of 1. So let's use the same shortcut as before and see if we can't find a value that works. We search the last row of the table for an answer that is equivalent to 1. And once again, we have a hit. For modulus 26, the inverse value of 9 is 3. So let's go ahead and replace 9 to the power of -1 with 3 and solve for A. When we find a solution, we end up with 15 mod 26, which is just the same as 15, and we now have the value for one of our keys. Let's find the value for the other key. So to do this, we simply grab one of our two equations, and again, it doesn't matter which one, and we substitute our A value to solve for B. And when we work it out, we come up with an answer of -315 mod 26. We enter this number into a calculator and we come up with a final answer of B equals 23. And look at that. At the beginning of this exercise, these were the two values we were looking for. And here are the two values we came up with. So you can see, as long as we know the mappings for at least 2 characters in the message, the Affine Cipher doesn't give us a whole lot of security. And that's it. In this video, I introduced the Affine Cipher and went over the details on how to encrypt and decrypt messages using a simple formula. At the end of this video, I went over 3 possible attacks that someone can use to break the Affine Cipher, including the brute force method, the frequency analysis method, and finally using simultaneous equations to solve for the encryption keys. I hope you enjoyed watching this, and I look forward to seeing you again in my next video.